All right, hi everyone. I'm Ekbal. I'm a remote sensing geoscientist at the British Geological Survey, and I'm going to give talk for about maybe half an hour or so. So, just a brief introduction about what we do at the BGS with satellites and satellite data. And really, I want to answer your questions. So, get your questions ready in your head, and at the end, we'll do a Q&A and ask me all you like about satellite data and what we can look at from space and why we do it. So first, let's start with this image. This is a famous image that many of you might have seen, actually. It's the first image of the Earth from the moon, and it's taken by astronaut Bill Anders on the Apollo 8 mission, which was the first mission that orbited the moon. It didn't land. It was the first one to get to the moon. And they just went around the moon a few times, it came back. And this is a really beautiful image because it's what we call an Earthrise. So in the morning, if you're at the beach, you see the sunrise. The sunrise is above the horizon, and it's a beautiful image. This is exactly the same, but the Earth rising above the horizon of the moon, and this image is called an Earthrise, and it's quite a famous photo. And there've been other ones since, but this was the first, and I think it's quite beautiful. But where did it all begin? Earth observation, like looking at things from space. So this is where it started, really. This part of the American and the Russian space race. The Russians were the first to put a satellite into orbit around the Earth. And there was this thing, it was called Sputnik 1. It looked like a weird beetle thing. And it didn't do much. It went up into orbit and crashed back down to Earth a few hours later. The first image from space was taken by this satellite. It was called Explorer 6. And it was sent into orbit by the Americans in 1959. And it's quite a small satellite by today's standards. It was about 64 kilograms in size. But it took the first image from space, and this is what it took. And I hope you'll agree with me, it is a pretty terrible image. It's blurry. It's like the kind of photo my dad takes if you give him a camera. And of all the places in the world to take the first image from space, it is of a cloud in the middle of the Pacific Ocean. So it's not very spectacular, not very interesting either, but it is the first image from orbit and therefore of historical importance. But obviously since then, the cameras have improved and we can do so much more now since then, and that's really what this talk is about. So, well, since the last 60 odd years now, we've been putting satellites up into space almost every year. And now there are several thousand satellites orbiting the Earth, and they do take all manner of measurements about the health and state of the planet. And really, but really, there are two types of satellites. The first type are satellites that look out into the vastness of the universe and the solar system itself. And this is probably the most famous of them all, the Hubble Space Telescope, which was launched into orbit in 1990. And incredibly, this satellite was only meant to live for 5 years. And to this day, 30 years later, it is still taking images of the universe and sending images back. And which is an incredible achievement from an engineering point of view, that this thing has lasted 6 times its recommended lifetime. This is one of the most famous, for me, it's my favorite Hubble space image, and it's this beautiful part of the Eagle Nebula, and it's called the Pillars of Creation. And this is a gigantic, enormous cloud of dust where new stars are being born. So these huge clouds are coalescing, and you can see some little blue sparks inside them where new stars are being born. They're coalescing and condensing and forming new suns. And I love this image. It's spectacular what we can do with cameras in space. But that's not the purpose of this talk. This talk today is about looking down, the second type of satellites. So there are a whole set of satellites in space that their only job is to not look out into the universe, it's to look down at the Earth. And this is one of them. This is the European Space Agency's Sentinel-3 satellite. And this is an image it took a couple of years ago. Oh, I think this was last year. This is an image of Japan. It's beautiful, rich green colors of the island forests and the seas. And this is big, if you can see my mouse, this blue this gray patch here is Tokyo. Oops. This huge gray patch is Tokyo. Tokyo is a gigantic urban city, and you can see this from space. So what else can we see from space? This is another image taken by Sentinel-2 of Mozambique and of the Zambezi Delta. And I love this image because you can see the river emptying out into the Indian Ocean. And if you look carefully, you can see the ancient shoreline of Mozambique here. This is the ancient shoreline of Mozambique. But over the last several thousand years, this river has been emptying out into the ocean. All the sediment is collected in the land and dumping it out to the sea. And it has extended the country by there now today. So all that sediment coming out of the ocean, out of the rivers, has been dumped at sea and has made the country bigger over time. And I love that you can see things like this from space. Another interesting thing in this image, you might notice, the eagle eyes among you, are these strange things. And these little blobs, these dark blobs there, they're wildfires. And you can see these fires from space. They're big enough to see from space. And an interesting question we can ask by looking at this image is, when this photo was taken on 20th September 2016, what direction was the wind blowing? And if you look at the plumes coming out of the fires, you can tell that the plumes going from there southwards. So the wind is coming from the north and blowing south. Those are interesting. These are the kind of interesting detective work we can play when we look at images like this. Here's another one. This is unfortunately a false color image. So this isn't the true color, it's the false color image of the Flinders Range in Australia. And the way we color these things is how the light reflects back off the ground. So it's not just random color. These colors represent how the light is reflected back off the ground. And what that really means is it's coloring each of the geological layers in the ground. So this is a way of mapping the geology from space. All we do is see how the light reflects off, and you see all the different layers of geology. And this mountain range is 500 million years old, and it's been eroded away now. You can see all the folds and the bends and the wavy patterns the rocks have made. So you can use this to map geology, and in fact we do it. One of my colleagues is using this exact technique to look for lithium rocks in South America. We find all this lithium rock, we mine it out, and then the lithium goes to power the technologies that we use today. So these are all very useful tricks and techniques we apply in our work. We also could look at the poles. This is Antarctica, the imagery iceberg that broke off East Antarctica last year. And so this is a gigantic iceberg that broke off in the matter of 7 days. So look at the dates at the bottom, 20th of September and 27th of September. So this iceberg broke off East Antarctica, and it's absolutely enormous. When I say enormous, this is the size of Greater London in comparison. This iceberg was larger than the Greater London. And so this is increasingly a problem now, and it's a problem because some of these routes, not this one, but in West Antarctica, are shipping routes. So with satellites, we can monitor these giant icebergs and prevent the 21st century Titanic from happening. Another big use for satellites is mapping and monitoring our rainforests. So this is an image of Western Brazil, Southwest Brazil, and it was taken in the year 2000, so it's about 20 years old. And you can already see the green bits of the forest, Amazon rainforest, and all these brown patches are where they've cut away the forest for plantations mostly, actually, and for dairy herds, for cow herds. And if you look at another photo, 12 years later, this is how much forest has been lost in just 12 years. And in fact, we can measure how much forest has been lost over the last 30 years, just by looking at these images. And we think over the last 30 years, just in this part of Brazil alone, southwest Brazil, an area the size of half of England has been cut away from the Amazon rainforest. So, that's the power of satellites. We can look at large areas and make these sort of measurements. More recently, this is January this year, in January 2020, a map of the air pollution. If you look at the map here, this is the boot of Italy. And so this is northern Italy. This is a map of air pollution in northern Italy in 2020. And this is the normal, it's really bad. And we know that air pollution is a problem. And this is what air pollution is like in northern Italy normally. But this is what happened in March. The air pollution levels dropped drastically in northern Italy. And this is because Italy went into a lockdown because of the coronavirus. So the coronavirus, we could see the impact of it from space in terms of air pollution in this case. And this gives, and we can see the same patterns happen in China and actually in England and Germany as well. This is a really cool image. I love these images. This is night lights, what we call our black marble. So this is a photograph of the Earth at night. And if you're good with geography, you might not recognize where this is. There's this map here. This is Japan with Tokyo there. And this is the eastern coastline of China with Shanghai there. Hong Kong is just there, and this is Taiwan. This blob here is South Korea. And this dark patch here is North Korea. North Korea has no lights. I'm going to zoom into that just to look at more detail. So this here is South Korea, this bright patch here, this really bright blob is Seoul, the capital of South Korea. And it's doing what we expect for a big capital. This is about the size of London. So London never really sleeps. It has lights on, street lights, cars, everything going on at night. And these you can see from space. And this is what we expect. Seoul is very bright at night. And that's the capital of South Korea. And to the north, that is the Pyongyang, the capital of North Korea. So it's not very bright at all, is it? And the rest of Korea, North Korea, is actually dark. There is very little electricity. So what we're seeing here is poverty. Despite how much we see in the news, North Korea is very poor and it doesn't have electricity everywhere. And at night, you see this stark contrast between South Korea and North Korea. And another interesting feature is this line here you see. This is the border between North and South Korea, the demilitarized zone, this patch of forest full of mines and fences. And you can see it from space. And it really marks the boundary between the two countries. So this is geopolitics from space. This is probably my favorite image of all from space. And I'll explain what it is. This is a photo taken by a satellite in 1990 from deep space. And that little white dot there is Earth. And so it's probably one of the most iconic images ever taken of Earth. And it was taken by the Voyager 1 satellite. So this satellite went into orbit it was sent out into deep space in 1976, I think. And it was just sent off straight into deep space. And by 1990, it got so far away, it was just about to leave the solar system. That's about 6 billion kilometers away. And just as it was about to leave, the NASA astronauts said, just turn the cameras back and take one last photo of Earth as it leaves the solar system. And this is the photo it took. And Carl Sagan wrote a wonderful piece about it, and you can read about it if you Google this image. And it's the pale blue dot. It's called the pale blue dot. And it's officially the longest space selfie ever taken, in my mind. And it's going to be hard to beat. But it's a beautiful image. So let's step back a little. So I've spoken a lot about space. And so let's ask a very simple question. Where does space start? It sounds like an easy question, but it's actually quite hard. Let's look at this image here. This is obviously of the Earth. This inky blackness is space. And this fine blue mist on top of the Earth is our atmosphere. Our atmosphere is quite thin, actually. And it contains all the gases and the water vapor that we need to survive as a species. And so technically, space starts where the atmosphere ends. But if you look at this image, it's a bit fuzzy. It's hard to put a line saying, this is exactly where space starts, and this is exactly where the atmosphere ends. So it's actually quite tricky to make that measurement, say this is space. So to make it easier for us, the international space community have got together in their big committees and said, we're going to define the start of space. We're going to make a definition. And what they've said is that space starts 100 kilometers above the Earth's surface, technically above sea level, 100 kilometers. So that's the official definition of outer space. So how far is 100 kilometers? I live in Nottingham, so I live in the Nottingham, and I've drawn a circle 100 kilometers wide around where I live in Nottingham. So this is how far space is away from us. If I got into my car and drove in a straight line from Nottingham all the way to Skegness to the beach, I'd have driven the same distance it takes to get to space. So if I could do it, if I get in my car and drive upwards, I would get into space. But if I drove the same distance as it takes me to get to Skegness or Shrewsbury or Worcester. So actually space is not that far at all. It's not far away. So why is it so expensive to get there? And that's because gravity. We have to escape the pull of gravity to get into space. And that's why we need things like this, rockets. And actually, the satellites that we send into space are all located in this top tiny bit at the top, the cone. That's where the satellite is. The rest of this rocket is just full of fuel to burn and escape the pull of gravity. And not only to burn, it's to get you fast enough to get into orbit. So actually, it's all about gravity and speed rather than distance to get into space. So I've made a little animation to tell you about how we do it. So this is Earth, this is my little mini rocket. And if you watch these launch videos, the rockets go up first and they turn sideways quite quickly. So getting to space isn't about going up, it's about going horizontally as fast as you can. So this is what happens, it goes sideways. And it's building up speed until it gets to the edge. And then what happens? It doesn't fall off. By this point, hopefully, it's gathered enough speed that it can swing around and continue going and getting to orbit. So this is how satellites get into orbit. They don't go up, they go horizontal. And they get faster and faster and faster until they can swing around, until they get this balance between the gravity and speed. And they need to get to around 10,000 miles an hour, at least, to get into orbit. So getting to orbit is essentially a controlled way of falling off the Earth, really. And what do they do when they get up there? They do their job. Satellites turn on, point their instruments down, and take measurements of the Earth. They look at the Earth, and that's their entire role. But how do they look? How do we look, in fact? We look by using light. Light bounces off things and enters our eyes. And you might remember this figure from school classes. It's of the electromagnetic spectrum. And it's how light travels through space. Think of light as ripples on a pond. And you can see the ripples start in the middle and they move out towards the edge of the pond. And sometimes you have big ripples, sometimes you have small ripples. And that's exactly how light works. It can move in big ripples or small ripples. And on the right here, you see the big ripples, the radio waves. This is how radios work. They use the big ripples. And if you go left on this graph, you get smaller and smaller ripples. So from the radios, you go to microwaves. This is how microwaves work. This is where radar and communication satellites work. Infrared is heat. And this is where we see. This tiny little bit here is all that we can see with our eyes. The visible light, green, yellow, red, yellow, green, blue. But there's ultraviolet after that, ultraviolet, the X-rays, and there's gamma rays. So we only see a tiny fraction of what light actually does. But satellites can see it all. So this is why satellites are really useful. And in fact, we've sent satellites up in space to exploit this whole spectrum. So the radio waves are generally used by telecommunication satellites. And in fact, the British Ministry of Defence has a whole network of satellites in space called Skynet. And those of you of a certain generation who've watched Terminator will know that might give you a sense of doom. But Skynet was actually launched before the Terminator film. So Terminator stole it from the Ministry of Defence, which isn't that comforting either, to be honest. But yes, the British government has a network of satellites called Skynet. Next, microwaves. Microwaves are generally used by weather satellites. And every day you get your weather alerts from the news. And these weather modeling stations use a lot of satellite data to track clouds, track rainfall, track temperature and pressure from space. And this is a big industry. Infrared is all about heat. So when someone talks about infrared measurements, they're talking about heat measurements. And we can make heat measurements from space. This is what this NASA image has done at the bottom here. It's measured the heat of the oceans. Red is hot ocean, blue and purple are cold ocean. And you see around the equators, the waters are hot, but not in all those strange sort of patterns. And you can follow all the ocean currents using these heat maps of the ocean, which is pretty cool. Then we have the visible, the light that we see. And this essentially is like sticking a camera on a satellite and taking a photograph. And we do this a lot as well. Ultraviolet, X-rays and gamma rays tend not to be used to look at the Earth. They're more for deep space exploration or looking at the sun and things like that. So with satellites, we can see the Earth in many more ways than just using our eyes. And that's the power of using these technologies. We can see much more. So how do we at the BGS use satellite images? So we use it to monitor changes in the Earth's surface, including monitoring the growth of cities. We use it to build digital models of the Earth. We use satellite images to respond to disasters like volcanic eruptions, landslides, and earthquakes. We use it to monitor the Earth's magnetic field and to monitor space weather, which I'll talk about later. And we also use it for mineral exploration. Like I said earlier, how about looking for lithium and other interesting rocks that have commercial interests. So I'm going to give you a few examples of how we have used satellite images in the past and how we use it today. This is a spy satellite image of eastern Chile, eastern Santiago, the capital of Chile in South America. And I'll talk a little bit more about these spy satellites in a minute, but suffice to say, this is an image from 1970 of eastern Santiago. This is the same area in 2014. So if I show you the images side by side, you might see some small differences. I've shown these in yellow here. This hill on the left in 1970 was just a hill. In 2014, it's full of houses. These are rich houses on the mountains with big swimming pools. Same here on the middle one. And these are the fields in the south and bottom one where now have houses on them. And that's the city expanding, city growing out eastwards up into the mountains. But there is a problem here. The city is growing eastwards onto the mountains, but this red line here is a fracture in the ground called a fault that can have earthquakes. But this fault hasn't had an earthquake in 8,000 years, but it's still possible to have one. In fact, we think it's due one soon. So now, over the last 100 years, the city has grown over this fault. Now, all these people who live on this mountainside are in danger of this big earthquake that could happen on this fault. So it's put more people at risk, and we can see this risk growing as the cities expand over onto the fault. So back up with the spy satellites. So amazingly, in 1960s, 70s, and 50s, late 50s, the Americans launched a whole network of satellites into space called Corona. And what they were doing with it was basically spying on everyone. And they were spying on mostly Russia and China, but not only that, most of the world. And at the time, it was all very secret and confidential. But now we can talk about it because it's all declassified. We can talk about these things now. And what was really cool in the 60s and 70s, obviously they didn't have digital networks, so they couldn't beam the data down. What they had to do was stick it in little canisters and eject it out of the satellite. And they had their Air Force plane fly around with a big net, basically, to try and catch these little canisters as they fell out of space, which is incredible if you think about it. In the 1960s, they were doing this. Now they're probably more sophisticated, but we're not allowed to talk about it. Then one important thing I need to talk about is resolution, satellite resolution. And what that means is, what's the smallest thing we can see from space? And in the 70s and 60s, the spy satellite could see something about 2 meters in size. That's about the size of a small car. That's what people could, the military could see in the 60s. They could track your car, basically. Now we can see something as big as 30 centimeters. That's about the size of an open book. So theoretically, we can see books open, but we can't read the text on it with satellites. These are satellites that are publicly available. And this is what we can do with this kind of satellites. A few months ago, you might have heard in the news, there was a big oil tank that got stuck on the coast of Mauritius. And the Worldview satellites from Maxar groups went over and imaged it. So this is the satellite here. This is the tanker here on the coast of Mauritius. That's the coral reef where it got stuck. This is mainland Mauritius. And these satellites are so powerful, we can keep zooming in. So let's zoom in a little bit more. This is the oil tanker, and using that same image, just zooming in. We'll zoom in again, and you can see all the details on the tanker. You can't actually zoom in one more time. I don't have that high image, but you can then see all the boxes and crates on the sides of the ship here. This is the detail we can see from space. This is about 700 kilometers in space, these satellites. So they're really powerful. And for events like this, they really help, disasters. We can monitor the oil spill coming out of this from space. And this is just using public satellite. You can buy the satellite, anyone can go online and buy the satellite images. And the military have their own things that Lord only knows what they do with it. So what else can we do with space? We can monitor, we can figure out how much stuff you need to grow a city. This is what we're doing in Hanoi, the capital of Vietnam. Vietnam is this long country in the east of Asia, and Hanoi is its capital up here in this yellow star. And Hanoi sits in this big delta area. It's where the big Red River Delta sort of ends in the South China Sea. And Hanoi sits here. Zoom in a bit more. This is Hanoi, this is the Red River. It sort of straddles the river. And we were interested in measuring how much stuff do you need for that city to grow, particularly how much concrete. Because cities grow by more concrete growing out, roads, tarmacs, buildings, etc. And it's a city of 8 million people and still growing today. So my colleague at the BGS ran some really clever computer algorithms on the satellite data to try and count how much of the city is concrete, how much of the city is field, how much of the city is forest, water, etc. And this is the map he created in 2013. The red is concrete, yellow is field, green is forest, and blue is water. He did the same in 2018. And in fact, he did for every year up to the 80s and 70s. And this image here, 1972 is on the right, and now is on the left here. And this is just of the concrete surfaces. And you can see the concrete surfaces in Hanoi have been growing in time. So what we can do now, we know how much concrete is growing in the city. We can figure out how much concrete they will need to keep growing the city. So this is the power of things that we could do with satellite data. Something else we can do is make use of parallax. Now, we all intuitively know parallax. If you hold up your finger in front of you, close one eye and close the other eye, and alternatively close one eye at a time, you see your finger move slightly. And that's because you're looking at the same thing from slightly different angles. And that tells you, that's the way of getting 3D information about what we can do. We can use this same technique with satellites. So instead of having two eyes, we obviously have one satellite, but we use that same satellite to take the image of the same thing at slightly different times. And it's almost exactly like having two eyes. And we can play this trick and draw 3D models of the Earth. This is what we did in Santiago. On the left is the satellite image, and on the right is the 3D digital model of the ground that we created. It doesn't look very impressive here, but you can drape it onto Google Earth, and it looks a little bit more impressive here. What's cool with this is, because it's digital, we can strip out things. We can strip out the buildings, we can remove the trees, and we can just look at the ground. So this is the ground with all the buildings removed. And now you can see all the little hillocks on the side here, the little bumps. Those bumps is exactly where the earthquake fault is. And that was before hidden away underneath the concrete of the buildings and the woodlands and the forests. And by having a digital model, we can strip out those and find where those earthquake faults are. And you know, if you have a 3D printer, you can print it out in 3D like this, and it's really helpful. So basically, these 3D models help us look for those tiny little telltale signs in the geology, in the ground, that's indications of ancient landslides and earthquakes that really help us understand how people are in danger. The other thing we've done is respond to tsunamis. We respond to disasters regularly at the BGS. And this is what we did in Indonesia a couple of years ago. There was a big earthquake and tsunami, and my colleagues went out there, but also did some satellite mapping. So on the red line here is my colleague who drew the old coastline of this part of Indonesia. This is where the old coastline was. And the blue line here is where the current coastline is after the tsunami. And you can see the tsunami sort of washed away this entire harbor. It's just destroyed it all and washed it away. And this yellow, this green line is where the tsunami water came up to, and all the buildings up to that were destroyed. Same again here. This entire harbor area here in red is completely destroyed and washed away by the tsunami. So we use this satellite to map these things, and they help us to understand where the damage is and where we think people are in danger, and it helps you to find, search and rescue and all that in the event of a disaster. We did the same in 2018. There was a big volcanic eruption at the Krakatoa volcano. Some of you might have heard of this volcano before, Krakatoa even. And this was an ancient volcano that erupted 100 years ago, and it blew off everything. But this is the baby of it. And it's not a baby anymore, it's actually quite a large volcano. Here it is. And in 2018, it erupted, and half of the volcano exploded. You can see here, nearly half of the volcano has disappeared. It literally vaporized itself and created a really big tsunami and killed about 400 people in Indonesia. So, and my colleague has been monitoring this volcano and seeing how it's growing back. In fact, this is what the volcano looks like now. And all these lines are how much magma has come out of the volcano after the initial explosion and regrown the island. And in fact, he showed that within a few months, even though half of the volcano was vaporized in the eruption, within a few months, the island itself grew by more than 10% of its pre-eruption size. So that's pretty incredible how you can monitor all this from space. The other thing that I do particularly is radar. Radar is an ancient technique that, many of you will know about, this where this beam swipes around and is measuring time, and you can find things far away. And we can stick a radar on a satellite, we can do the exact same thing. We can send beams of microwaves to the Earth and measure the time it gets to get back. And we can do this regularly, continuously, every 6 days in Europe and every 12 days for the rest of the world. We can take a radar image of the ground. And what this does, lets us to find small changes in the ground that are happening over time. And with this technique, what we're doing is to measure how cities are changing, in particular how cities are sinking in Indonesia. And this is our target city at the moment. It's Bandung. It's about a city of 2 million people. It's about the size of Birmingham. And over the last several decades, its city has been sinking. And this is the result from our radar data analysis. The blue colors here tells you how much the city is sinking by. Yellow is not much. Blue is a lot. In fact, this city is sinking by about 15 centimeters every single year. That's half a length of a normal school ruler. Right? So in 1 year, a city the size of Birmingham sinks into the ground by about 15 centimeters. That's a lot. That's a lot. Right? And why is this happening? It's because Bandung is one of the biggest cities in Indonesia with textile industry. So what they're doing, all these big garment industries are pumping water out of the ground to feed the textile industry and buy all the clothes that you and I wear, because a lot of these clothes get exported, some of them to Europe. We wear these clothes, and because they're pumping so much water out of the ground, there's lots of space left underground, and the city is sinking into it. So we can see all these things happening from space. The BGS also has this amazing thing. It's called our Space Laser Facility in southern England. What it is essentially is a giant laser on the ground, and its job is to look into the sky and fire lasers, this rather large laser at passing satellites over the UK. And this is a really strong laser. I mean, it's so strong that someone has to be there 24/7 in case we burn the eyeballs off airplane pilots. It's pretty dangerous. So, there's 24/7 manned people there just in case. What we're doing is actually just firing at satellites, not to destroy the satellites, but what we do is we fire the laser at the satellite as it fires over and measure how long it takes for the laser beam to bounce back. And that tells us exactly the height of that satellite, the orbit height. And it helps us to monitor the orbits of satellites and making sure none of them are doing any strange things up there. And basically, it's just a ray gun. It's just the closest equivalent we have to a giant ray gun. And it's pretty cool. The other thing we do is measure geomagnetic storms. So now, every now and then, the sun has a little bit of a hissy fit and belches this gigantic burps and releases this huge storm cloud of really high energy particles that's just like a wind of horribleness that gets sent out into the solar system. And these are huge, huge belches. In fact, they're so big, that's the size of the Earth in comparison. These things are enormous, and they belch out a huge ton of stuff into the Earth, towards the Earth. And if it wasn't, and this is what they do, they give this beautiful aurora. And this is because the Earth's magnetic field protects us from it. That's why we don't get vaporized by it every single time these things happen. So the Earth's magnetic field sort of guide these particles around the Earth and safely protect us from all these really dangerous particles. But these really strong flares can affect our electricity and our navigation systems. And so BGS scientists are involved in monitoring our magnetic field, see how it's changing, because it's always changing. We monitor the magnetic field and give warnings about how any solar flares might affect us and our technology. And part of that, to do that, we use satellites, particularly this set of satellites called SWARM. And what they're doing is constantly monitoring the Earth's magnetic field just to make sure what's happening, and we can fit our models correctly to it to help us monitor how and where we might get affected by the next solar flare. And to do that, we'll give space weather warnings. So like you have your weather warnings on Earth, like it's going to rain tonight or it's going to be sunny tomorrow. The BGS gives a daily space weather, telling you how the solar activity is changing, how it might affect us on the ground. And you can go onto our website to find out more about this there. So that's it really. That's just a flavor of what we do with satellites. I mean, we do very little, of course, but there are thousands and thousands of satellites out there, and they do so many different things. And really, this is just the beginning. We want to monitor the health and well-being of the Earth from space. And it's thanks to all these satellite companies, these are just a few of them, that we can do that. And one of the great things is much of this satellite data is free. We don't have to pay for much of this data. And so, what a time to live in. Thank you. Right, let me end this and we can start some questions. Okay, so what's the best way to do it? I think the best way to ask your questions is to use the question and answer feature on Zoom. So if you have any questions, please type them in and I'll try and answer them. I can't promise I'll know all the answers. So a question about accessing satellite data. How do you go about getting access to the data from satellites? Do you mainly use pre-existing data, or do you have direct access to satellites to gather your own? So we mostly use data so we don't run our own satellites. Most of the satellites are run by space agencies, but we have access to the data that they collect. Sometimes we have to pay for it. Most of the time we get it for free. And because the UK government is part of the European Space Agency, we have access to all the European satellite data for free. Sometimes we buy satellite data from other space agencies like the Japanese or the Germans or the Italians, but a lot of the NASA's data is also for free. So it's amazing what you can do with free data. But if you want the really, really high resolution stuff, like I said, the 30 centimeter, you need to buy that stuff. Another question. What is the what's the turnaround time for obtaining useful information and responding to natural disaster satellite data? So that depends on the satellite you're talking about. So the Sentinel data from the European Space Agency we get that within 3 days. So a satellite, any one part of the ground will be measured within about 3 days' time. So from the time the satellite takes the image to us getting it, it's about a few hours. So from the time it takes for the satellite to take the data and give it to us, it's about 4 hours, I think. But that's just using one satellite, but there are thousands out there. So every time there's a disaster of some sort anywhere, all the space agencies in the world go into like high alert mode, and they say, okay, turn all our satellites on and point it at that place where there's a disaster. And then you get a whole load of data from all over the world. And that's really quite quick. And so that's a real power. When you start working together with everyone, you can really respond to disasters quite quickly with satellite data. How do you deal with cloud cover with satellite images? So that's a really big problem. So with optical data, if you had a camera in space, just normal camera, if there's a cloud, you're in trouble. You can't see the ground because you can't see through a cloud. But with the other satellite, other images like the radar can see through clouds because it's a slightly longer wavelength. You can see all the way through clouds. So this is what I use a lot. And radar works at night as well. So you don't actually need sunlight to work with radar images. So we have different, depending on what the situation is, we use different types of satellites. So I work with radar data, which can work at night, and it can look through clouds. But if you want to look at optical data, you can't do it at night, you can't do it over clouds. I showed an image of the lights from urban areas at night. Can you see the heat signatures from these urban areas? Yes, we can. So we can see the heat signatures. So I showed you the heat map of the oceans. We can also do a heat map of the land and see, and in fact, the weather stations do this a lot. We can see how the cities are heating up, and we call this heat island. And yes, so we can do that. We can find out, but the tricky with heat on land is that the heat isn't, you can see the heat from cities, but also the continents heat up by themselves anyway. The sunlight makes the ground heat up. So it's a little bit more tricky doing heat measurements on land than it is over the oceans. Can we monitor in real time live satellite images? We're getting towards that. We can't at the moment, but we are getting towards that. There are new generations of satellites going into space that have live footage all the time. But this is the real frontier now. This is just all experimental at the moment, but soon, hopefully, in the next 5-10 years, we'll be able to monitor live things happening in space. So that means we can monitor, even now, we can monitor illegal fishing, we can monitor just pirates in the oceans, we can monitor oil spills and all that stuff happening around the world. So imagine if we could do live, there's your pirate ship, go and catch it, kind of thing. Can airplanes only fly inside the atmosphere, or can only rockets go outside? Airplanes can only fly in the atmosphere, indeed. Airplanes need, the way they fly is because they push against the air and it creates this pressure difference along the wing. And if you don't have an atmosphere, you can't have a pressure difference. So airplanes can only fly in the atmosphere. Rockets can go out of the atmosphere because they don't rely on the air pressure difference across the wing of a plane. Or the way they get out of that, they fly is just burning lots of fuel. And it's very, very expensive. So rockets can fly in the atmosphere, but it's not good because all the friction just means you have to burn more fuel. So rockets want to get out of the atmosphere as quickly as they can because then they don't have any friction to slow them down. Can you tell me about INSAR and its job opportunities? So INSAR is that technique I was talking about earlier about using radar images, satellite radar images, and taking lots of images many times every 12 days and building up this sinking cities map. So that's the technique we call INSAR. INSAR, it's big now. We can monitor. So what we can monitor is millimeter level changes on the Earth so the satellite is 700 kilometers away in space, and we can measure millimeter level changes on the ground. So it's like if I was in Paris and watching, if I was sitting in Paris and watching you move your finger in Manchester, that's what we're talking about, the level of detail we can get from space. It's incredible. And it's sort of revolutionizing how we can work now and monitor things from space. Yes, it's a great, if you want to get into a job, it's great. It's a big industry these days. So I recommend you to learn a little bit about the technique if you're at a university. And a lot of companies are starting to employ graduates with these skills now. And so I recommend it. Please email me directly if you want specific details of any interesting things you want to learn about that technique. What subject did you study to do a fascinating job? Thank you very much. So my career path has been quite strange. When I was at school, I was interested in space. I wanted to study the universe and the cosmology, the planets and all that stuff. So I went to university to study space. But when I got to university, I found out that actually space is interesting, but the Earth is even more interesting. The geology of our planet is so fascinating. I'm fascinated by earthquakes and volcanoes and how tectonic plates work. So I decided to bring both of my passions together, space and Earth, and do remote sensing, which is looking at the space, looking at Earth from space. And so I studied, in school I did maths, physics, chemistry, and in university I did geology, and then I did my PhD in geophysics and satellite geodesy. It's been brilliant, and now I get to not only look at the Earth and space, but also try and solve those big problems that we're affected by, like how do we solve poverty, how do we solve climate change? And those are the big questions now that we're trying to handle with bring all our skills together. Into the future, what do you think will be the biggest innovation to come? Oh, that's a good question. I think someone alluded to this earlier, this live data. If we can get live data of the Earth all the time, that means we can monitor things all the time. Like how we can respond to disasters instantly. We can save lives that much quicker. A few seconds can make a difference in a disaster. So I think that's a big innovation. And also the big innovation at the moment is, this is a bit technical, but big data. These satellite images are huge. We have a dedicated computer server at the BGS to process all this. And we're talking about, so the server I have is 100 terabytes in memory, 100 terabytes, and 200 gigabytes in RAM, those who understand these computing terms. And this is just about coping. I think the big innovation will come with how to deal with all this big data, all this huge volume of data. We need programming software that can handle all this. And that's the future, I think. If you see something in the data that is sensitive, secretive, do you have a responsibility to communicate this? That depends what you see, I suppose. We can monitor things like North Korean explosions from space, and my colleagues have done that. We don't have the responsibility to communicate it, because if we've seen it, the military have almost definitely seen it too. So because we're like civilian scientists, the military and the governments have all their own secretive ways of monitoring the rest of us, but we don't have responsibility to report it now. How much data can you get from one satellite? We can get a lot. It depends which satellite as well. So one of those radar satellite images I told you about was 4 gigabytes in size, and I use hundreds of them. So it's a huge volume on your computer. I mean, your laptop would not handle it. You need a really big computer to just store the data, let alone process it. In terms of information, we can get all manner of information, from what side is the sun on, where is the wind blowing, how hot is that house compared to your house, how busy is this street, and therefore you can monitor traffic from space, and you can sort of design cities so that traffic flows better. So you can do all manner of cool things. But from a geological perspective, you can measure where are the faults that will have the big earthquake, where are those landslides that are just about to slip and cause a devastation downhill, or you can monitor, like I said, sinking cities. Where are the people pumping too much water out of the ground to make the whole ground sink to the ground? So that for me is where it's interesting, where the people and geology sort of interact with the ground. How long does it take to get to space? So getting to space, like I said, it isn't very long. You have to get up 100 kilometers. So it actually takes just a few minutes to get up to 100 kilometers. But getting into orbit takes a little bit longer, because you have to not only go up, remember, you have to go horizontal. And you have to go horizontal to at least 10,000 miles an hour. So it spends a lot of fuel just going horizontal, getting up to speed. So it could be, so it takes a few hours to get into a proper orbit around the Earth. How far away do you have to be from the sun before you get burnt? That's a really good question, and it depends. So if I go to space now, I won't get burnt because I'm a little bit far away. But obviously, the closer you get, the hotter, the more exposed you are to sunlight. And I don't know exactly how far it is that you can safely go. I wouldn't recommend too close. For example, if you're at, this is a really good example. If you look at the planet Mercury, which is the closest planet to the sun, half of the planet is facing the sun and half the planet isn't, right? The half of the planet that is facing the sun gets full sunlight, and that's around, oh gosh, I don't remember off the top of my head, but it's around 400 degrees Celsius. It's really hot, basically. 400 degrees on the side that's facing the sun. On the other side, on the same planet, that's just in its shadow, it's about minus 14 degrees Celsius. So just simply being the shadow makes a huge difference, regardless of how close you are to the sun. So it's really fascinating. Who invented satellites and how are they made? Satellites, well, okay, we've always dreamt about going into space, haven't we? And even in the ancient Greeks, they looked up to the sky and said, imagine if we could get to the moon. Imagine if we could get to the stars. So we've always wanted to invent satellites. And really, the key thing was about after the World Wars, after 1945, the first thing we sent into space was around about the wartime, after the war. And funny enough, we sort of stole a lot of German missiles after the war. We sort of pinched, well, the Americans pinched, but the British too, pinched a lot of German missiles, V2 engines. And what they did was they sort of reconfigured them to send things into space. And that's where it all started, really, after the war. So it hasn't been long at all. And it's all about, sending things to space isn't difficult. You just need a cone with lots of fuel. It's just staying there that's the hard bit, and not falling down again. Can you tell about INSAR application to disaster management? Okay, so INSAR is that technique I spoke about earlier, measuring those small changes in the ground surface from space. So INSAR, to do INSAR, all it is, you have to take a radar image before the disaster and after the disaster. And all you do is see what's changed from before to after. What's the difference? What's changed? And so if there's an earthquake, you can see where the ground has moved. And then you can send people, say, okay, there's a lot of ground motion happen there. That's where all the landslides are happening. That's where we think most people will be affected. So you can send people to areas that you think are high risk. This is what we did in Nepal in 2015 after that big earthquake. Most people were focusing in the capital city, in Kathmandu, but we saw that the earthquake was much bigger than people thought. And so in the west of the country, in the high mountain areas, there were loads of landslides that the disaster people had missed. So then not just us, but the INSAR community said, look, you're missing all these people there that are also need your help. You can see it from space. So you send people and say, look, that's where they need lots of help over there. So it's really helpful for search and rescue, really. But then also about how that has the ground relaxing over time, so that we say, okay, don't build your house here. This place is still dangerous. We can see it from space. So it has an important role to play in the whole management cycle of disasters. Can we make geological maps from satellite images? Do we need all data to remove urban structures? We can make geological maps, and we do. And so I showed that example of Australia, and we do exactly the same thing in England and in Brazil, not Brazil, sorry, in South America, in Bolivia, to look for lithium rocks with lithium in it, so we can mine it for our batteries in our phones. So we do, and it's actually quite a big part of what we do. They do it in Africa a lot, and it helps to have old data. It always helps to have old data, and we're lucky because the British Geological Survey is the oldest geological survey in the world. We're over 150 years old, and we have lots and lots of old maps. And if it wasn't coronavirus, I would invite you all to come and look at our old maps. They're really beautiful. We have old maps of all over the world, not everywhere in the world, but a lot of places around the world. And we can compare the geological maps from today that we make with satellites to the old maps we did 100 years ago by people walking around these fields and mapping it out. So it really helps that we can do both. How can satellites see so much detail from so far away? Well, that's the amazing thing, isn't it? Our technology these days is so powerful. We can see something that's only 30 centimeters in size from 500 kilometers away in space. It's incredible what we can do. And that's just the power of technology. And it's only getting better. Sooner or later, we'll be able to see better and better things with space. And by the time you guys have gone to university or decide to start working, we'll have done better. The new innovation these days is not to have really big satellites, it's to have lots of small ones. So like satellites are about half a meter by half a meter in size. So instead of sending one giant one, you send 50 small ones. And you can make them work together like an ant swarm. How ants work together in a big swarm, you can do the exact same thing with satellites. Instead of having one big one, you have lots of small ones and they work together. And that's the really cool stuff that's happening at the moment in space. How much money does it take to send a satellite to space? They are very expensive, very, very. So just taking it to space is millions of pounds. So just because that rocket needs so much fuel, it just costs millions of pounds just to get the satellite into space. But building the satellite also takes a lot of money because we have to spend lots of time making the satellite, understanding, doing the research. And so it's a lot of money. But we in the UK are one of the world's best at making satellites, believe it or not. And despite what you think the Americans might think, we are also very good at making satellites in the UK. So if it's an industry you want to work in, then we have lots of great people in the UK who can help you get into this and get work in satellite making. How about space trash? Do satellites pick up on how much there is floating around? How is it cleaned up? Yeah, so this is a really big issue. There are lots of junk. There's a lot of junk in space, unfortunately. And most of it is because of old satellites that have died and just kept up there. All the new satellites that we send into space now, they have a requirement that when it's time for them to stop, they get pushed into the Earth's atmosphere and then they burn up. And so that's all the new satellites are required to burn up at the end of their lifetime. All the old ones that are left are causing all this rubbish in space. That's an issue now. It's a growing issue. And there are new satellites going up there now to help monitor this. And there are new research projects on how can we deal with it. And it's interesting. We can think about throwing nets out and and catching these big space junk and pushing it into the Earth so it burns up in the atmosphere. But it is a very big issue. And it's something that we're thinking about and how we should deal with it. Not just BGS, but the world as a whole. But at least all the new satellites are required to burn up in the atmosphere when they're finished. Why do you use a laser? So we use a laser because lasers don't die very easy. So if you're trying to torch, for example, if you go at night trying to torch, and if you go, the further you go, the dimmer and dimmer it gets, torches, right? Because they lose their energy. Because torches, they sort of scatter off and they just lose their light. And if you walk far enough away, that torch is just really hard to see. With lasers, they're really hard to lose their energy. So they can stay strong for quite a long distance. That's why lasers are so powerful. In fact, we can shoot a laser and bounce it off a mirror on the moon. In fact, that's what they do. And we do that quite regularly. The BGS doesn't. NASA does it a lot. They put mirrors on the moon, and every now and then they'll fire a laser and bounce it off the moon just to make sure the moon's in the right place. You can measure how far the moon is. And so we do it, the exact same technique, but not as far as the moon, but just as a passing satellite. And lasers just don't lose their energy. It means we can hit it, satellite, and get it back without making it too dim. What should I do after a master's in geology to be an INSAR specialist? It depends, actually. If you've already done INSAR in your master's, then that's all you need. You can start getting some work experience working with INSAR. If you're interested in solving scientific problems with INSAR, then maybe a PhD is the right thing for you. So it's hard to say because I don't know how much INSAR you've learned and what you want to do with it. I happen to do a PhD in INSAR, but that's not the only way to get into it. You can just do, like you said, a master's or a bachelor's, and then just start working with using INSAR. Do any countries have a magnetic shield? Interesting. No, we don't. We don't have, no single country has a magnetic shield, but the Earth has its own magnetic shield. The magnetic field of the Earth itself is a shield, and it's what protects us from all those horrible sun rays, the powerful ones that come out of those solar flares. So no single country has its own, but the Earth has its own one, and we're monitoring it constantly at the BGS with our satellites and our computer modeling. When the rocket comes down, how does it land? Well, there's only one company and country in the world that can land a rocket, and that's SpaceX in the US. And they're the only ones at the moment who can take a rocket into space and bring it down and land it. And they land it on land or on a boat in the sea. So if you're interested in that, do just Google them. They're incredible how they do it. It is mind-blowing. But most of the rockets, when they've released a satellite into orbit, they come back down and land in the oceans. And they land in the ocean in a safe space. So we'll make sure there aren't going to be any ships or any boats or anything like that. And they just land it in the oceans. And sometimes they're recovered, sometimes they just let them sink into the bottom. How do you own a satellite? Well, you have to build it. If you build it, you own it, don't you? And like I said, it doesn't take much to build one. It does take a lot to build it. It takes a lot of scientific and engineering expertise, and that takes time. And in the UK, some of the big satellite company makers are Airbus, the guys who make the planes in the UK. They also make satellites in the UK. And they're just a big company, and they make them. And so we at the BGS don't own a satellite. No, we don't. We just use the data from them, from other big satellite companies. Do you have satellites which can strip cities and forests? Can you go under the ground, strip layers of rock? See, that would be amazing. No, we can't. We can strip cities and forests. So yes to the first half of your question. So like I showed you before with the satellite, where we made a 3D map of the world, of the city. For that, we made a 3D map, and we could take away the forest, we can take away the buildings, and just look at the bare ground. What we can't do is look into the ground from space, and that's, for now, we can't do that. But we can look into the ground from the ground, and this is the science of seismology, which is the bread and butter of geologists, right? It's like listening to the ground, and with seismometers, and you can build up this image of what the ground looks like underneath your feet. So we can look into the ground, but not from space. Not yet, anyway. How will we launch rockets to space when fuel in the world runs out? So this is a good question. So it takes a lot of fuel to take a rocket to space. And thankfully, we're not going to run out of fuel. Thankfully, we're not going to run out of fuel anytime soon. And not at least for the foreseeable future. But eventually, we'll have to think of more environmentally friendly ways to get to space, because it burns a lot of fuel. And hopefully you guys will be the ones to discover that. How do we get to space in an environmentally friendly way? Currently we can't. What is the typical lifespan of satellites? How would they be superseded by new satellites with more advanced sensors? So yes, so the typical lifetime of a satellite is anything between 3 years to 10 years. But like I said, the Hubble space satellite was meant to be up there for 5 years, and it lasted for 30 years. So sometimes they last a lot longer than they're meant to. But yes, so it's about 3 to 10 years. That's in general the lifetime of a satellite. And when it's over, and the lifetime's over, and we think it's just about done its job, all this fuel's gone, then they enter it into the Earth's atmosphere and it burns up. So it doesn't leave any waste in space. And obviously, we're always continuously making new discoveries and new developments. So the cameras are getting better and better and better and all that stuff. So after 5 years, if they want to continue the mission, they'll send a new satellite up that's got a slightly better camera on it. And they keep doing that. They keep cycling the new ones in each time. But the way these space agencies work is what they put on the satellite is really, really, really good. So what they're putting on the satellites now, you'll see in your phones in about 5 years' time, because the technology in satellites way better than we have in our phones now. So the satellites that come from us now, that technology will be in your phones in 5 years' time. So they're not always behind the technology. They're the ones actually who make the technology that then eventually gets to us in our everyday phones and laptops and things like that. Why do satellites don't crash since there are so many? How does one get rid of space junk which are not usable? So it's true that they don't crash very often. They don't crash often because space is very big. I mean, believe it or not, although there are many satellites up there, several thousand, and lots of thousands of pieces of junk, space is still really, really big. You know, there's a lot of space up there. And for now, the chances of crashing into each other is really low. And also because all the space companies that have satellites really, really carefully map where their orbits are. And they're constantly mapping against other space agencies, seeing, okay, their satellite's over here, mine's over here. The chances of collision are really low. When hitting junk, that's a bigger problem. In fact, yesterday, a big satellite came within 25 meters of another one, a dead one, a junk one, and a good one. They came within 25 meters of each other. So that's really, really close in space. 25 meters is really, and that was dangerous. And that's going to be a bigger and bigger problem with time. So we really need to get rid of those big junk pieces. And so there's lots of research now on how we can do that. And for now, no one has the answer yet, but we'll get there, I think. How do rockets fly up so fast? They fly up so fast because we burn a lot of fuel. It's like, think of a jet engine and then times it by 1,000,000 and add 9 of them. That's how much engine, that's a lot of power behind a rocket. You're basically sticking a cylinder with a lot of dynamite in the bottom of it. And that's how it goes. It burns a lot of fuel really, really quickly to get you up to such high speeds. What is the furthest place an astronaut has got to? That's a good question. I don't know the exact answer, but I imagine it's the moon. We haven't been anywhere further than the moon, have we, as a human species, as people? But we have sent satellites out quite far. And the one I showed you earlier about the pale blue dot, the image taken from 6 billion kilometers away, that's the furthest thing that we've ever sent as a man-made object. But there are obviously no people on it, it's just the satellite itself. And we sent that off in 1976, over 40 years ago now, 50 almost. And you know, it's gone so far away. It's gone past Jupiter, it's gone past Saturn, it's gone past Uranus and Neptune. It flew past Pluto. Now it's past the solar system and it's gone out into deep space. That's the furthest object, man-made object in the universe at the moment. But there aren't any people on it. The furthest a person has gone is the moon, for now. Maybe we'll send people to Mars soon. If a satellite is to fall to Earth, what would worst place scenario? So yes, if it falls on the city, then it's dangerous, of course. But that's rare because we are constantly monitoring satellites, not just for how they're performing, but how dangerous it is if they were to fall. And for those really big satellites that don't burn up in the atmosphere, they're just too big to burn up. What we do is there's a graveyard in the southern Pacific Ocean. In the south of the Pacific, it's like the loneliest part of the ocean. No ships go there, nothing, no human live there or anything like that. It's just a bit of the ocean that's really boring and nothing there other than obviously the sea life. And that's called the satellite graveyard. If we really need to make a satellite fall into the Earth, we drop it there in the southern Pacific, as far away from any people or boats as we can get. If Jupiter is a gas planet, how did the storm form? That's a really, really good question. And I have no idea. And I don't think anyone knows either. And so those are the kinds of questions that make a good scientist, because no one knows the answers. And we really need more people to ask those questions so they can help us figure it out. So that storm on Jupiter is really old. It's big. It's bigger, like 50 times the size of the Earth. and or through, I don't know, it's quite big. It's much bigger than the Earth, and we don't know how it's formed. It's a really good question, and I don't know. When there is a heat wave, why does thunder and lightning come after the heat wave? That's a good question. So thunder and lightning happen because of it's static electricity. So you might have done this in school. So electricity charges are positive or negative. When it's hot, air rises from the oceans, usually in steam, and it gathers into these clouds. And they have a charge. Sometimes it's negative, sometimes it's positive. It's charged storm clouds. And when they all get really big and they fly up and they gather up towards the land, they bump into each other. So, but if a negatively charged storm cloud hits a positively charged storm cloud, then they spark. Negative and positive spark. And when they rub against each other, they make electricity. And that electricity then connects with the negative charge of the Earth, and it creates a pathway from the storm cloud, the negative charged storm cloud, to that's the other way, the positive charged storm cloud to negative charged Earth. It makes a pathway for the lightning to come down. What happens to satellites after lasting their working life? What about this huge ironic creation of the space one? Huge ironic creations around space and Earth. After lasting their working life, most satellites are burnt up in the atmosphere. They are, when we're finished, the satellite's done its job, we deorbit it. We make it go down and we just burn it up. And it all just disintegrates and just disappears, vanishes, it burns up. And that's what happened to most satellites as they come to the end of their life. A few more questions. I'll answer these before I head off. When you get the data, how does it get sent to you? We get the data through the internet, believe it or not. It gets sent to us through the internet, basically. In the old days, I say old days, say 10 years ago, 15 years ago, we used to get them on big floppy disks, not floppy, sorry, CD drives. But these days, you can get all the data through the internet, through not email, but internet pipelines. What would happen if we didn't have satellites? That's a good question. Can you imagine what would happen if we didn't have satellites? Can you imagine a life where we didn't have GPS on your cars? Can you imagine what we would do if we couldn't fly a plane? Because planes use satellites. Can you imagine if we couldn't sail a boat? Because boats use satellites data to help navigate. Can you imagine? The world would be a very different place, wouldn't it, if we couldn't do all those things, if we couldn't travel, if we couldn't fly, if we couldn't sail. So it's hard to imagine now, isn't it? Could a satellite ever get a picture of a black hole? Yes, and that's a great question, because this year was the first time ever we took a picture of a black hole. And you can Google it, and it's absolutely incredible. We know that black holes exist, and we have done for 30, 40 years now. And in fact, this year's Nobel Prize in Physics, if you read about it online, was awarded to those people who did black hole research. But this year was the first time, or was last year? No, sorry, last year. It was last year. Was the first time we took an image of a black hole, and you can see it on the internet if you Google it. It's really, really cool. And this is the future. We're going to see all these things in the future. What was the biggest volcanic eruption in the world? Oh, that's a good question. And I don't know. I don't know what it is. My volcano friends will definitely be able to answer that one, but I don't know. I'm sorry. I suspect it's one on the. No, I wouldn't be able to know off the top of my head. Sorry. Is the Earth's magnetic changed over time? Yes, it does. The Earth's magnetic field changes all the time, continuously, and which is kind of really annoying actually sometimes, because like places like New Zealand have to continue. We have to always change their coordinate system because their GPS always. And actually, funny enough, earlier last year, and the entire country of Australia had to change its location because they looked at the GPS and they figured out, oh, actually, the whole country is 1 meter in the wrong place. Because of the GPS measurements, they realized, oh, actually, we think the whole country is in the wrong place, so they had to move it a little bit. not the country, but on the maps. So the GPS always help us, but yeah, the magnetic field is always changing, and we need to monitor it. Can satellites be recharged using solar energy? Yes, they do. Can satellites be recharged using solar energy? Yes. Big satellites have solar panels on them because we can't always have fuel on them, so we need solar panels. And that's why they can last for 5-10 years. It's not because we have lots of fuel on it, it's because we have solar panels that help power the electronics. That means the energy and the fuel can be saved for flying and not powering all the electronics. Thank you. Thank you for all the questions. Wow. I think we will end it there. Please email us if you have any more questions, and I'd love to continue chatting and hearing about what you think. But thanks everyone, and we'll call it an end there.
Thank you for the fantastic talk, Ekbal.
Thank you.